It is my great pleasure to introduce Professor Ylva Götberg. I'm sorry I cannot be there in person due to traveling, but I'm happy she's presenting at EF4 as we are collaborators and very good friends. Uh, Ylva is from Sweden, where she did her bachelor and master in Lund, but she also went for a couple of years in Grenoble too to study her master there. She then moved to Amsterdam at 2014, where she did her PhD on the evolution of massive stars in binaries with Dr. Selma de Ming. That's also what I did. So we met there and we were together during our PhD years. After her PhD, she went to US with the Alvin Nashman and subsequently the prestigious Hubble Fellowship in the Carnegie Observatories in Pasadena. And a couple of years ago, she has moved back to Europe as an assistant professor at the new ISTA Research Institute in Vienna, in Austria. And in general, Ylva is an expert in stream helium stars in binaries that are formed after mass transfer in binaries. First of all, by modeling them, but she's heavily involved in observationally detecting the first sample of them. That's something that was awaited from, I think, all the binary people. And it's very important that we start finding them. And Ylva is one of the person heavily responsible for this. So with that, I want you to give the floor. Thank you for being here. By the way, Ylva is in Creta because there is a conference starting tomorrow, I think, in Chania. So we have the pleasure to have her for the day. So the floor is yours, Ylva.
Thank you, Mano. Let's see, we'll move him to the other screen. And thank you all for coming. I'm really happy to be here and to be able to visit the Institute, at least even if it's just for a day. My name is Ylva, and as Mano said, I work with interacting binaries. I tried to depict this here in the background of the title slide. This is an image that's supposed to show you how binary stars interact. It's not something really small. It's actually a lot of material being dumped onto another star. So it's not a tiny thing. It's a major change of life. I'm going to talk a little bit about envelope stripped stars today and how we built a theory that we could move from just theory to the observation of such objects. It's one of my favorite topics. So if you have questions, you can definitely ask me. I work together with Maria Drought from University of Toronto mostly. She's one of my closest collaborators. And so we started this work together, the observational effort. She had then a student, Bethany, who is now a postdoc in Leuven, and current student, Alex, whose work I will also show today. And part of this is also my undergraduate student, Beryl, who is now a PhD student at Northwestern University in Chicago. I work at the Institute of Science and Technology, Austria, or ISTA for short. This is the campus, and we have just recently started this little group of interacting binaries. Since they are all very new, we don't have any results just yet, but maybe next time I can show you some results from these new group members. So the outline for today, I will start with a little bit of an introduction so that we all can feel comfortable with binary stars. I suppose not everybody works with binary stars here, so then I thought that was nice. And then we're going to talk a little bit about the importance of these envelope stripped stars or helium stars. Why do they matter, and for what? Then we will move towards the discovery of this missing type of object and end with a little bit of a new touch from Alex, mostly on the binary properties. But to begin with, I'm sure you have been faced with this kind of graphic. This is an artist's impression of stellar evolution from NASA. What they are showing is that stars evolve according to their mass from a blue object moving maybe through some giant phases, then there is some kind of ejecta and you create a compact object. It looks rather simple. It is simplified. In some cases, one may even say this is wrong. So why do I say that? I think this figure is showing you the main reason. It is work by Max Moe and Rosanne Di Stefano, where they synthesize. Each data point here is a major observational survey. So it's actually quite a lot of work involved in this tiny little plot. It shows you the fraction of stars that will interact in a binary system as function of the most massive star in that system. So for a solar type star, only about 15% of them interact with a binary companion. Given how many solar type stars there are, that's quite a lot. But this is an increasing fraction. So when you reach the massive stars, if you reach above 5 solar masses, the single stellar evolution pathway is no longer the normal stellar evolution pathway. The normal stellar evolution pathway is binary evolution. So what is binary evolution? What is binary interaction? This pie chart is giving a broad idea. Actually, it's from the one of the data points in the previous plot. It's for massive O stars in the galaxy. Ugsana and collaborators, they did a survey of massive O stars in the Milky Way, looking for how many of them have a binary companion, what is the mass of that binary companion, and what's the separation between these two stars. With that, Selma de Mink could forward model what will happen with these stars in that binary, and found that actually the majority of these stars are going to interact with the companion. Only about a third of them evolve basically as single stars. And these three major groups, the envelope stripping, mass accretion, and even merger, are all significant differences of the stellar evolution pathway, resulting in a variety of different things. We will not go so much into detail. This was just to show that it can be quite fun when you work with binaries. There is quite a lot of things you can do. I will focus on this third here, the envelope stripping part, and talk a little bit about what does that mean, what's the outcome, and why we care about that. So just so that we are all on the same page here, I have a video. Manos has seen it many times, but maybe it can help the audience in the room to feel more comfortable with what is envelope stripping. So what just happened? We had two stars in the binary. The most massive star on the left-hand side, it evolves first. It has the most fuel, it burns the most vigorously, it evolves first. It tries to become a red supergiant, but then at some point during this expansion phase, the outer layers of this star starts to feel a stronger gravitational pull to the companion star than to itself. This initiates mass transfer. In this case, I drew the graphic so that the mass transfer stream is such that it hits the surface of the companion star, but because we have an orbital motion, it doesn't hit exactly on the center. It hits a little bit off center, and you initiate the spin up of this star. What is left of the donor star is the hot and compact helium core now exposed. This is what I usually call a stripped star, a helium star, a stripped envelope star. There is many different names. So if you encounter something in the literature that sounds like it could be that, it's most probably that. We haven't really converged yet. Actually, mass transfer is something that has been seen. This is observations. This is interferometric observations of Beta Lyrae. Beta Lyrae is also called Sheliak. It's a star that has a name. It's at about 300 parsec distance, and it's a binary. As you can see, the dark star here is deformed into a drop-like shape. It's currently undergoing mass transfer. The dark star is the brightest. it's the donor. It has currently 3 solar masses, and the crater star, the companion, has 13 solar masses, and the orbital period is about 13 days. So this system has transferred a significant amount of material to the companion star already and is in the end phase. The observations are taken with the CHAR array, which is an interferometer, up in the mountains north of Pasadena, where I used to work, which is why I like to show this one, because you can just point. Yeah, it's actual images. So now let's move towards the importance of the stripped stars. And for this section, I have prepared a little bit of theoretical predictions. I come from theory background, stellar evolution modeling with MESA. Spectral modeling, I use a code called CMFGen for hot star spectra. And I have also prepared a spectral population synthesis code, but it's really basic. And it doesn't have a good name yet, but it's just to show proof of concept things. So let's start with a little bit of a recap of massive stellar evolution, just so that it all feel comfortable. This is a Hertzsprung-Russell diagram. It shows you the effective temperature in the reverse direction on the x-axis and the luminosity on the y-axis. We're going to follow a 12 solar mass single star here. It starts evolving to cooler temperatures and higher luminosity. And this happens during the main sequence when the star is fusing hydrogen to helium in the center. Then it expands a little bit and heats up a little bit in the center. After the main sequence, the star expands substantially, reaching very cool temperatures. And this is when it has depleted hydrogen in the center. The core, the helium core, starts to contract, igniting the hydrogen shell just above the core that causes an expansion. This is called the Hertzsprung gap. When it reaches the Hayashi track here, it starts a convective envelope. And at these later stages, as a red supergiant, this star continues fusion in the center, finally reaching an iron core. And here we think that it would explode as a hydrogen-rich supernova, since it has all of this envelope left, which could, and this part, I don't know whether it would be a neutron star or a black hole. I would guess neutron star. Probably Dimitris knows better. But let's put it in a binary, so to see what is the difference, no? So with the binary, the main sequence, you are accompanied here by the companion star, and this dashed line is showing an equipotential surface called the Roche lobe. When the star expands, it will feel its Roche lobe starting to transfer material here, and what is left is just this hot and compact helium core that actually is quite long-lived because it still has the helium core burning left. And it spends most of that here as a 4 solar mass stripped star at around 80,000 Kelvin surface temperature. So it becomes a really, really hot object, something that this 12 solar mass star would never have reached on its own. Only in a binary system you can reach such high temperatures. Later, in this case, it didn't have any hydrogen left, so it would be a hydrogen-poor supernova, maybe a 1b. And if you compare it with the single stellar evolution pathway, we completely change the evolution of this star through binary interaction. It did something completely different with its life. So in what cases does this matter? We can look, for example, at the gravitational wave progenitor evolutionary channel. This is the standard one I will walk you through from Thomas Tauris on how you create merging neutron stars. We start with 2 stars in a binary. Since they are so close, they start to interact. You do Roche lobe overflow mass transfer, creating a helium star. This is the first strip star that you create in the formation of merging neutron stars. It's made through stable mass transfer. The supernova here is a hydrogen-poor supernova. You're left with a neutron star, if you're lucky, neutron star plus main sequence star system. That can or cannot be a high mass X-ray binary at some point. But it should enter a second phase of interaction. In this case, it's considered a common envelope because you need to bring these two stars very close together for them in order to be able to merge in a gravitational wave event. So what is left after this common envelope ejection is a neutron star and a stripped star. This is the second stripped star you need. And that is created through a different channel, in this case, through the ejection of a common envelope. You can have interaction later on. Eventually, you create two neutron stars that can merge and create maybe a black hole, who knows? Yeah. Now, we also walked through a couple of cases here where there was a supernova involved. And the fact that you have lost most of the envelope through binary interaction is actually something that is going to affect the supernova. I have only one slide, but definitely recommend talking to Manos and Dimitris on this. But if we look here, it's a rather old pie chart of the fraction of core collapse supernovae that are hydrogen poor. It's about a third, which should ring some bells back to that graphic. About a third of all massive stars are stripped through envelope, mass transfer envelope stripping. Something else that may be of interest here is if we look at the ejecta masses from supernovae that are stripped envelope supernovae, these peak around 2 solar masses. It's rather low. This is something that you cannot have a very massive star exploding to do. It's actually most likely a lower mass star that then would have been stripped perhaps through its mass transfer. So this is just to show you why I think it's relevant to consider also the progenitor to the supernovae that we see today. I also am grateful to the supernova community because I think that they realized this much earlier than the stellar astrophysics community. That they realized the need to better understand the stripped stars because they are the progenitors. It was pretty clear to these envelope stripped stars. I have another part. We talked about progenitors to gravitational waves, but actually these little strip stars can also be gravitational wave sources themselves because they are so small that they actually fit in such a tight orbit that they can radiate gravitational waves. If we look at the gravitational wave frequency calculations, it's really rather simple. It's just 2 over the orbital period. So these compact object mergers, like the neutron star merger, they have the orbital periods of seconds. That translates to frequencies in the LIGO band. But in this case, you can have something like hours, which is about the LISA band. So I'm quite excited about the LISA launch because I think it's going to be really nice to be able to see gravitational waves from living sources. And I prepared some population models for how many we expect to be able to see. This is showing you the gravitational wave frequency and this gravitational wave string. In the, I think it's the light gray, we have the LISA sensitivity curve. So everything in the white is probably in the detectable zone. Here I'm comparing the blue part, which is the population synthesis of stripped stars with compact objects with double wide dwarfs. And in this simulation that is meant to simulate the Milky Way, we would get maybe 5 such systems. They could have maybe one with a neutron star, some with a white dwarf. I like all of them. But it's just to show that it could be nice and interesting to see. And they can be studied in advance because they are also optically luminous. No? They are not completely dark sources. So I've been talking quite a lot about these stripped stars, but it's actually often so that maybe the audience doesn't really, maybe haven't really heard about that. If I would ask, what type of spectrum does such a star have? What's the spectral type? Or what's the, how many of these objects should there be? This is not something that is very clear, right? So Beryl did a population synthesis study where we predict the number of these stripped stars. And to do this, she used this population synthesis code that is based on single and binary stellar evolution tracks that I interpolate. They have different metallicities, and it's a Monte Carlo code, so you randomly draw from initial distributions of initial masses, binary orbital period, binary fraction, mass ratio. We found one of the main important things to look at is actually the translation between the initial mass and the stripped star mass. This determines quite clearly how massive the stripped star will be, and therefore also how many you will have of different mass ranges. This graphic is showing in circles the ones that we adopted, and in the gray circles is a comparison with another work. So even if it looks small, this makes quite a big difference when you put that in a mass distribution plot. So this is now the mass distribution as function of the mass of the stripped star. And we find quite a bit more stripped stars compared to the Jungelsson et al. Collaboration. So what is right is, of course, a good question. I think that perhaps we overestimated a little bit the mass of the stripped star at the low mass end. But this is something that still needs to be observationally constrained. What Beryl also created, I think this plot is easier. This is an inverse cumulative distribution. So we have the stripped star mass on the x-axis and the cumulative distribution on the y-axis. So let me walk you through how to read it. If we're interested, for example, in stripped stars that are sufficiently massive to explode, this is something above 2.6 solar masses, according to Thomas Tauris. Then this plot says that we should have about 4,000 such systems for every solar mass, for every population that has a star formation rate of 1 solar mass per year. So we can convert this to expected numbers. So the Milky Way with a solar mass, with star formation rate of 2 solar mass per year, we would expect there to be about 8,000 explodable stripped stars at this moment. And the LMC and SMC, Large and Small Magellanic Clouds, have several hundreds of these objects at this moment. That, of course, depends on what we think is the true star formation rate and star formation history, but it's an order of magnitude estimate. And we did a comparison, actually, with the stripped envelope supernova rate in the Milky Way, which it was estimated from observations to be about 10 to the minus 6, 0.0067 per year. Whilst in our models, we have a little bit higher rate. So I think maybe we overestimated slightly the mass of the lowest mass stripped stars. But the other work I mentioned, they have a substantially lower rate. So yeah, we need a little bit more observations. This is just to give a handle on how many we think there would be. The status before 2023, we expected there to be this many stripped stars, but really this was the reality. So there was nothing observed in the Magellanic Cloud. We had one star in the Milky Way. This one is called HD 45166, that at the moment, before the work of Tomer Shinar, was thought to be a 4 solar mass stripped star. But Tomer then went to check it closer, realized it's magnetic, and it actually has a different orbital period that is very large, and it just got demoted in mass as well. So now it's like 2 solar masses, probably not going to explode. That's why there is a question mark. So there were 2 alternatives we could see. The first, maybe we got the theory wrong here. Maybe this is not happening after all. It's a little bit demotivating, because then we would need to rethink a little bit the supernova and the gravitational wave progenitors, and kind of a problem, no? So I decided to think that they were just a little bit hard to find. So let's try and identify these stars. And this is a work that I did start then together with Maria Draut. I should say that there are strip stars have been found in the low mass regime and in the high mass regime. So if we look here at the strip star mass, the neutron star progenitors are there in the middle, while the subdwarfs are down here. And subdwarfs we have seen. We compare this now with the companion star mass. There has been some observations of subdwarf and B-type systems that have been studied in quite detail. For example, another example from the Chara array, I think it is quite nice. What Robert Clement did was to look at rapidly rotating B-type stars, BE-type stars, and look for subdwarf companions to those by actually resolving the subdwarf. And then he could track where is the subdwarf, how is it moving around this BE star. So this is one example where you can actually see how the subdwarf is moving around the BE star. He has more of these systems. I think this one is nice because here you can see it's a slight eccentric. But all of these subdwarfs are quite low mass, something like 0.5 solar masses or so. So they are definitely not going to explode. Instead, where are the neutron star progenitors? So what me and Maria did was that we started to look at the spectral energy distribution of these stars. This is a model that I made of a 4 solar mass strip star, the one that we were looking at before. It has flux on the y-axis and wavelength on the x-axis. You can see that most of the light comes out in the ionizing regime. It's very hot, remember, 80,000 Kelvin. So we cannot observe there, but there is still light in the optical. Why is it that this is hard to see? Because there's often a companion star, no? So here I put a rather low mass companion together with this 4 solar mass strip star, a 5 solar mass companion. And you can see in the optical, actually, they have rather similar brightness, and they even have similar color. The slope is very similar. It's hard to distinguish. But if you look a comparison with the ultraviolet here, you should be able to see an excess radiation in the ultraviolet if you see either just the strip star on its own with a dark companion, or even with a companion like this. You should see such a UV excess. And we created this color magnitude diagram. It's really rather simple. It shows the UV brightness on the y-axis and the UV blueness on the x-axis. Here is the 0H mean sequence, and these are stellar evolution tracks for single stars, just for comparison. They evolve in this direction. They never really move blue wards of the 0H mean sequence. They don't move blue wards. Single stars don't do that. The strip stars, we expect to hang out over here during the helium core burning. So if we couple two of them, if we make that binary, it ends up there. And it should show a UV excess. It should turn up blue wards of the 0H mean sequence. You can make many different combinations, and these combinations should should end up blue wards of the 0H mean sequence, creating a discovery space. I should say not all combinations do this, only the ones where you have a rather faint companion, sufficiently faint that you can see the UV light from the strip star, because the majority of the bolometric luminosity from the strip star is emitted in even harder photons energies. So we don't know exactly what fraction of strip stars we can identify like this. I am guessing between 20 and 50%. But it's an order of magnitude estimate. It depends a bit on the efficiency of mass transfer, how much material is actually accreted, how easy it is to eject common envelopes, etc., things like this. So we decided to apply this to the Magellanic Clouds because we know what is the distance. We can easier measure what is the absolute magnitude of a star. The extinction is also low. So we used some data, archival data from the SWIFT satellite. And SWIFT actually, even if it is an X-ray telescope, it actually has a UV photometer as well. And every now and again, when it didn't have X-ray observations to do, took a little image of part of the Magellanic Cloud. So this is a nice data set. It just has rather large PSF, so we had some issues with crowding. And we compared this with optical images taken with the SWOPE telescope from Zaritsky itself. So this was the discovery space. This is the theoretical prediction. This is the actual observations. Here is the discovery part. And you can see that there is actually hundreds of candidates. Now, for the people who have worked with photometry, photometry is not always easy. And we don't believe that all of these, in fact, are stripped star systems. Some of them can be just misclassifying which star is which. Did we actually choose the right one? And did we maybe on mistake take 2 stars into 1? So you need to really look at the photometry and your targets before checking which one you think could be a good candidate. So that's why we have hundreds of candidates there. The Swift re-reduced data is soon to be out, and this is the work from Bethany Ludwig, the former PhD student of Maria. So this catalog is about to be submitted. Now, what we decided to do was to target the best photometric data, the candidates that we found here, blue Warsaw, the 0H main sequence, with spectroscopy. Yeah. So we used the MAGE instrument on the Magellan 6.5 meter telescope, through which I had access during my postdoc. This is a medium resolution spectrograph, about 4,000, and it covers rather blue. It goes even beyond 4,000 angstrom, which is really useful if you want to see signs from, for example, the B star. It's very strong Balmer lines over there. We started quite early on also to take multiple epochs spectra, because since they are binaries, we thought maybe eventually we will want to check that they are actually binaries. What we found to begin with was 3 different classes. We decided to I'm not very good at naming, so they are called class 1, 2, and 3, but they have different categories. So here, let me show you the class 1 and 2. They show lines of ionized helium. For a star to do that, it needs to be hotter than 30,000 Kelvin. This is also the boundary between the O and B type spectral classification. So for that to happen, it either needs to be an O star or it needs to be something else. And these are not bright enough to be O stars. So class 1 and 2 has helium-2 lines. Class 2 and 3 have substantial, strong Balmer lines here, short wavelength Balmer lines, which is typical for B-type stars. So what we think that we're looking at here is really on the top, the helium star type would be stripped stars that dominate the optical flux. Maybe they have a compact companion. The composite types, the class 2, would be those where we see both a stripped star and a B-type companion. This is presumably binary. And the class 3, the B-type, could be then when in those few cases in the optical, actually the B-type star is dominating the flux, but the stripped star is still sufficiently bright to provide a tiny bit of UV excess, making it possible to detect. We will focus today on the helium star type, mostly, simply because I found it easier to work with those. You can see the stripped star. There is not 2 stars, so you don't need to disentangle the spectra so much. But of course, also the others are interesting. It's just a little harder. I hope that you like spectra. I like spectra. I wanted to show you all of these spectra. This is the helium star types. Yeah, again, they are called star 1, 2, 3, yes. And they are characterized by highly ionized elements. So for example, here you can see helium-2 lines of ionized helium, and there is a lot of nitrogen lines, and it is not a low ionization, it's quite high ionization, nitrogen 3+, so nitrogen 4 lines, or nitrogen 4+, nitrogen 5 lines. This is indicative of very high temperature, but it's also indicative of CNO processed material. The CNO cycle is the nuclear reaction that helps massive stars fuse hydrogen to helium during the main sequence. And this is then a part of the star that will be exposed when you strip off the envelope. You will see helium-rich material, but also because the CNO cycle converts carbon and oxygen to nitrogen as a byproduct, you see nitrogen lines. So to figure out whether the stellar properties of these stars actually match our binary evolution models and our expectations for how stripped stars should look like, what their, if the models actually match, we decided to fit the spectra. This is star 6. Star 6 is a very nice star. I created a larger model grid that spans effective temperature, surface gravity, and surface helium abundance. Surface helium to hydrogen abundance is an interplay. And we fitted these 6 lines on top there and obtained a best fit effective temperature of about 75,000 Kelvin, a surface gravity of log G of 5. For comparison, main sequence stars have about 4. And the surface hydrogen mass fraction of 0.35. Now, this is not 0, no, it's not a pure helium star, but it's also not like main sequence stars that have something like 0.7. This is hydrogen poor, not hydrogen free. Tables are boring, I know, but I wanted to point out a few things. First, we believe the mass estimates we created are sufficiently high for most of these to actually explode. And given their surface mass fractions, we think that we both have hydrogen poor and the hydrogen free progenitors for the supernovae. Now, we haven't propagated their potential evolution yet, so that would need to be a future work to say that better. But we can put them in the Hertzsprung-Russell diagram. And so here is for the LMC and for the SMC. For comparison, I have put some Wolf-Rayet stars and marked a little bit the location, the rough location we expect for subdwarfs. This is where these objects end up. So it's somewhere in between the subdwarfs and Wolf-Rayet stars. And if we overlay stellar evolution models, this also seems to overlap with roughly the central helium burning during the strip star phase. Apart from maybe star 16, I think it's a little bit inflated, probably during the contraction phase. It's worth to note we would not have seen such a lower mass object unless it was cooler and therefore brighter. So on average, we think that the surface properties of these stars, they match the predictions from the binary stellar evolution models. And we think that we have created a little bridge between the subdwarfs and the Wolf-Rayet stars. How much time do I get? Do I have another 10 minutes? Yes? Okay, so then I will talk a little bit about winds. So stellar winds matter for the evolution of the star. If the star's wind is strong, you can create a hydrogen-free surface, for example, and it would change the supernova type. It would also change how much the star expands later on. Can it enter another interaction phase with its binary companion? But it's something that we didn't know very well. Usually it's parameterized like this. You have the mass loss rate, and that's with the bolometric luminosity. The Wolf-Rayet stars have a high mass loss rate, high luminosity, and the subdwarfs have low mass loss rate, low luminosity. Strip stars would be somewhere in between here, but this is really large parameter space, and we have very little models that can actually probe this part that tell us something. What I started to work with was extrapolation of the empirically determined Wolf-Rayet wind mass loss rate from Nugis and Lammers. But there is also this scheme that is a theoretical model that matches subdwarf wind mass loss. It doesn't go higher than about a few thousand solar luminosities, so cannot really use it so far there. This is a single temperature model. It's maybe the most appropriate. There is also follow-up work from the same authors, but it's really just for the massive helium stars. So I already mentioned that, yeah, why we should care about that. But so we have optical spectra so far, and you cannot do super much for wind mass loss rate with optical spectra. The most sensitive spectral lines for measuring wind mass loss is in the ultraviolet. So this is a project of my PhD student. He's having challenges with that right now. But what we did so far was to look at an alpha line in the optical. This is helium-24686. Again, star 6, so that we feel comfortable. And it's an absorption feature. The extrapolation for the Wolf-Rayet wind mass loss scheme, it predicts an emission feature. So I thought this is probably a bit too high mass loss rate. So let's decrease it, a factor of 10. This is something that would match roughly that a single temperature mass loss scheme. But it looks rather good than the zoom out version, but if you look closer, this still doesn't really match. So it's probably still a little bit too high, slightly too high. You need to go a factor of 100 lower in order to create something that kind of matches this profile. And this is not predicted by any existing model so far. So it seems like we have maybe a bit of a problem with the wind mass loss. And to better understand the wind mass loss would be really excellent at this point. Here is an example star 1 that has a little bit of wind infilling in this spectral line, and you can put a better constraint, and so it probably has a slightly higher mass loss rate, but it's still lower than what is expected from this Wolf-Rayet extrapolation. In total, they end up something like this. Nothing really matches. Let's keep in mind that these little data points here, they are upper limits, yeah? This is something that I mentioned, the PhD project of the Basic. Now, something that these weaker winds can do, and that I'm quite excited about, this was a short project by Benjamin Navarrete, was to try and look, how does it change the ionizing spectrum of this star? So he used some evolutionary models to compute the spectra, and here, the colored part to the left, this is showing you the bulk of the helium plus ionizing emission. So this is quite a lot, actually. And that is just because the winds, if they are now weaker than what we expect, they have a harder time to recombine, and therefore ionizing photons can leak through the atmosphere. This we thought was also quite exciting. So this is part of Beryl's paper. Where if we look at the emission rate of ionizing photons, if we focus on this light yellow, always told Beryl that the light yellow was not a good idea. If we fill in the new models, you can see that it actually matches quite well with this straight line, this new models from Benjamin. And if you convolve this with the population synthesis estimate, it actually means, depending a little bit on stellar evolution, this is why we have different sizes there. They either provide another 50% of, or they either double the helium plus ionizing emission rate, or they provide the majority of it. And this, I think, is quite fun and interesting to explore, because it could be a source that is responsible, for example, for helium-2 emission features in distant galaxies. Now, just to finish up, I have a short part on the binary properties, which is mainly the project of Alex Laroche. And so we're again going to look here at the helium star type, and first also a little bit the composites to show you a mystery. So with Alex, we define something that we call the delta RV max. What is it? We measure the radial velocity of the star at different points in time. Here, time, radial velocity. And you can see how the star moves. No? It moves in its orbit. The maximum extent here is delta RV max. So you don't have to fit an orbit. It's a really observational thing. Shorter periods have higher delta RV max. higher mass companions give higher delta R max. Inclination effects as well. We can make a cumulative plot, and the helium star types, they end up something like this. Whilst the composites, this is why Alex does not work with composites right now, they have a much different distribution. We don't understand exactly what is going on here. It could be that they had a different evolutionary background, could be that they are different in another way. This we just don't know. So there's various different reasons. But to look just at the helium star types and try and figure out what's the orbit of these systems is what Alex is doing now. To do this, he's using a rejection sampling code that is called the Joker. And what you feed into the Joker is initial distributions of orbits. So you sample the prior distribution range and reject the orbits that don't match the observations. So to give you an idea of how it looks like, here we have the time we observe the stars and the radial velocity of star 1 in this case. This is with 5 epochs. So we have not rejected very many orbits. It's completely purple here. This is how the eccentricity period diagram looks like for those orbits. So it's in the longer period range, but we don't know exactly. With 7 epochs, you constrain a little bit more, 10, 15, and thereafter about 20 plus epochs was what we needed to constrain this orbit. We think that it is hanging out there in the parameter spectrum. With this orbit, we can calculate the mass function. This is from the orbital solution, period, amplitude. And the inclination and the companion mass, this is degenerate with each other. So what we do, we assume a random inclination. And then what we get up is a distribution. So for this star 1, that is rather massive, we think its companion is about 4 solar masses. And this is then using the best fit spectroscopic mass. Yes. So we did this for different stars. We have 6 orbits so far, and 2 of them we have a lot of data, but it's just not working. One doesn't seem to move very much, and the other one, we always need to tilt the telescope. I think we're going to give up there. Star 8 also needs more epochs, but it's really faint, so I don't know if it's worth it right now. This means that our binary fraction is about 2/3, yeah. So it could be higher, but we have not managed to get it higher yet. And it's also clear that this to measure the orbital solution, we needed some delta RV max higher than 30 kilometers per second. So it works for those over there. So this is also a complication for the composite types. The companion masses are between about 1 and 4 solar masses. And so to go back to this parameter space, I think we can add some stars here now. I like it. We'll move the question mark. And we think that the companions, they likely have solar mass, that their light contribution is not strong enough, therefore can be hidden. There is one star number 3, that has a very tight orbit, so you cannot actually fit a main sequence star in that. It must have a compact companion. And what we're working on right now, and this is postdoc Dandan Wei is working on understanding the evolutionary background. What was it that actually led to these systems now when we have orbital solutions? But that is upcoming work. So to summarize, what happened was that stripped stars were thought to be very common, one of the most common type of evolutionary pathways for massive stars. Important for neutron star mergers, very poor supernovae. And we identified a way to find some of these systems, and the observed stars have broad agreement between the expected properties and the observed properties. And the orbits, they seem to range from hours to years. I didn't say that. Star 1 has a very long orbit. The others have quite short orbits. And the companion could be both regular star or compact star. So with that, I have reached the end of the presentation, and I'm happy to take any questions. Thank you so much.
I have actually two questions. One question is, given the strong helium-2 emission, would you expect to have any helium-2 ionized regions like helium-2 rings around those stars? Does anybody look for those?
Exciting. So let's see. Maybe let me go back to that slide. So this is quite recent stuff that I did together with Benjamin. And he worked here with a more massive end. And I think it's true, probably, for the most massive of these stripped stars, that there is enough helium plus ionizing emission to create a helium plus bubble, helium-2 plus bubble. But if you go a little bit lower mass, it could be that it's still too cool to do this. But I'm not entirely sure. I actually wanted to pick the brains of Dimitris to help me with that. But yeah, I think it's an interesting idea. We have a couple of stars that show O3 bubbles. But helium-2 is weaker than O3. So we're going to need to have a student who likes to look at 2D spectra, to stack stuff there and see if we can actually see something. That would be amazing. Yes. I think since the stars are in the Magellanic Clouds, we would need to have a very good resolution of that. Maybe Muse can do it. Can it go sub-arc seconds?
Oh.
Wow. It's a good case. Thank you for that.
So the other thing I was wondering, you showed the strong contribution of these big stars in the helium-2 budget of
yes.
And how about things I'm wondering is how much these big stars will contribute to some ionized products for the formation arrays that we get from its application.
Here you can feel safe. This is only about 5% extra contribution.
Okay.
Yes. So, and I find this reassuring that I don't have to say something that completely changes the star formation rate estimates. I don't know what they would believe me. But so the hydrogen ionizing emission rate from the strip stars is high. And the advantage is also that it comes a little bit after the star formation is mostly done. So this can leak through the gas. But most of the produced hydrogen ionizing photons come from still massive O stars.
Okay.
Yeah.
I have a general question. Yeah, so this is from the area results. How do we determine observationally the supernova rate?
Oh, sorry, that was me. Okay, I can tell you what I did, and you can tell me if it's nonsense. Let's see, where is that slide? Here. Right. So what we did was to look what is the rough rate of stripped envelope supernova compared to core collapse supernova. And then we have already an estimate for the supernova rate in the Milky Way. I just convolve this. So, I mean, the models is easy. No, that's just counting how many of them are more massive than 2.6 solar masses. But it was something really back of the envelope thing.
like errors, like, I don't know, it's 0.0067, okay, plus minus, like, do you have errors?
No, I have a twiddle in front instead. No. No, it's really just a rough number. It's not the main result. It's just to verify if it would be roughly the order of magnitude. I think it's a little bit, I don't think that they fully agree. Yeah, I think we have it slightly off, but I don't think it's super far off. I would have been concerned if I was like an order of magnitude off, no?
So how do you use the predictions for that? So, would you expect to see, would you have the sensitivity to see any of those systems outside the galaxy, like the Magellan clouds, or in
No, unfortunately, they are not loud enough. It's a pity.
Okay, thanks.
Thank you.
Nice to meet you.